Welcome to today's class about paragraph 3.3, building blocks of substances. There's a couple of topics we'll talk about today. I've noted them down here on the whiteboard. First we'll talk a little bit about molecules and atoms. After that, the molecular model, the three phases of which substances can be in, and finally a very small bit of theory about mixtures. So let's dive right in to the first topic, molecules and atoms. First, a little bit of a general idea about molecules. So molecules is something of which a substance is made of. And for example, we've got a glass of water here, and well, clearly the water is a liquid and it moves around. We can drink it, and it's good for us. Most of our body is made up of water. But what is water exactly? Well, if we zoom a little bit in, and with a little bit I mean actually quite a bit, we can see these water particles, and these are all molecules of water, and you can see they consist of a red sphere connected to two blue spheres. Well, these molecules are very, very small. We can't even see them with the naked eye. So we have to zoom in really, really much. And if we zoom in even more on just one simple water particle, which is one molecule, we again can see we have got one big sphere with an O, oxygen, and two smaller spheres connected to it with an H, hydrogen. So this is called H2O because we have two H and one O. But what exactly are these spheres and how do they work? Well, to talk about that a little bit more, we're going to make a difference between molecules and atoms. First of all, molecules, that's the particles which substances consist of. As you saw in the previous image, we have water, and water consists of all those connections, of all those spheres connected to each other and then floating through each other. And well, as I said, one singular molecule looks like this. Atoms are the particles of which molecules are made of. So these three spheres together are a water molecule, H2O, but each sphere individually is an atom. So we have one O atom and we have two separate H atoms. That's here as an example. And during class, we might also have a little practical way you can build with these spheres. I have an example here. And we have a little white ball, and we have a little bit bigger red one. And these represent the H and the O. So the bigger red sphere is an O atom, and we could connect one of these white hydrogen atoms with a little connector item. So if we pop it right in, and we do that same here, and we use a second set to make a complete H2O or water molecule. So this is how we can represent the different molecules and atoms. Well, this is all very good and very well, but atoms, what exactly are those? Well, those are the building blocks, the real building blocks of the substances. And there's a certain amount of atoms that we have, and we have a table called the periodic table with an overview of all the discovered atoms, or in other words, some people also use discovered elements. So I'll show that on the next slide. However, very important to know, you do not have to know this by heart, because there's 92 naturally occurring atoms, but the human beings, with all their science and research, we've actually made 118 atoms in total. Some of these are very good, and some of these are not so good for you. Some of them really like to stick around and stay as they are, and others don't really like it and they fall apart, but that's something for an entirely different video. However, the periodic table shows you all the discovered atoms. And what does it look like? Well, it looks like this. Very impressive at first glance, maybe, but really it's quite simple. We start all the way over here with hydrogen. Hydrogen is the first atom, and you just read it. The numbers go from left to right, so this next one is helium, all the way over here. Then you go to the next row: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and so on. As you can see, all of these atoms have a certain abbreviation, either with one or with two letters. Again, you don't have to know these by heart. The only ones you have to know, for me at the moment, are H, hydrogen, O, oxygen, and in a moment I'll also show an example of with C, that's carbon. So, molecular model. Well, that's the second item on the list, but the molecular model, well, what is it exactly? Well, maybe we should start with what's a model. Well, a physics model is a simplified representation of a very complex situation. And this may sound very strange at first and very confusing. However, as you could see at the start, we have water, then we had the water molecules all through each other, and then you saw the molecule, one singular molecule with individual atoms connected to each other. And this is the example of that water molecule. However, this is a very simplified version of how it really works in nature, because in nature you don't have a circle with a sphere with two holes in it, so you can poke a little connector, a piece of plastic in to connect it to other spheres. No, it works way more complex than that. So in order to make it a little bit more clear for everybody, we have a molecular model. With the molecular model, we represent the atoms as spheres and the connections between the atoms as a line. So we can easily identify which atoms are involved and how they are connected to each other. Well, in the book that we use, they have it a little bit different, because there they represent molecules as spheres. So if you have this singular water molecule, it's just one big sphere in the book. However, it's important to know that difference. When you have one big sphere, in the book they really mean just one molecule. However, for us it's a sphere is a singular atom. Very important. So between molecules there will never be a connecting line. Molecules never are tied to each other with a physical connection. However, and I'll talk about it a little bit later, they do attract each other. So, in the book, molecules can be represented as spheres. Between the molecules there's an empty space. So, if you have one molecule of water and you have another one over here, in between is literally nothing. There's no air, there's no water, there's nothing. Very important to realize. Because we're working on such a small scale, you can't see the individual molecules. Yeah? There's literally nothing in between the water molecules themselves? Well, molecules themselves, they do move. Just like we do. We move around, so do molecules. And like us, if we walk on the busy street, we sometimes bump into each other. That happens. Same happens with molecules. So they can bump another molecule, give off energy, and that way there's also some interaction between the two molecules and within a certain substance. Important to know, the higher the temperature, the faster the molecule moves. So this is very important to remember. When it's very cold, molecules tend to be very still. They don't move that much. However, when the temperature gets higher, they start to move more, and that way they bump into each other more often and with more energy. So they give off more energy as well. So that in turn also makes a little bit of a difference, and we'll talk about it also later when we're talking about the phases of substances. And finally, as I said, molecules don't have a physical connection, so they are not tied together. However, they do attract to each other. A little bit like magnets. A magnet also attracts to another magnet, and if they're close, the closer they are, the more they attract each other. If they're stuck together, you have to use a lot of force to pull them apart, and then the further you are, the less the magnetic influence is. So the same works with molecules. Molecules, when they're very close together, they like to stay together, and if they are a little bit further apart, they don't really have a one big cohesion. Oh, it's more of a freely moving substance. Very important to realize, if they move faster, they need more energy because they collide with each other. So the distance grows apart, so the molecules attract less. And we'll use that for the next part, which are the three phases of which a substance can be part of, can be existing. So as I said, all substances exist in three different forms, and their forms are called phases. And I think all of us know them. However, it's very good to have a clear list of what they are. So the first one is a solid phase, and I think we all know this by ice. If you put water in the freezer, it freezes, it becomes ice. So it goes from liquid water to solid water, which is ice. And very important, when we're talking about the molecular model, molecules vibrate close to each other in a fixed position and attract each other strongly. So because it's very cold, when you have ice, it's very cold, the water molecules don't move that much. And if they don't move that much, they also use up less space, so they're close to each other, so they attract each other more strongly. And when they attract each other more strongly, they tend to have a fixed position. It's a bit the same if you have a really busy classroom. Yeah, if all places are taken, then you don't necessarily move from place to place. However, if you have a lot of free spots, free seats in the classroom, you might ask, oh, well, I like to work with another person. So you start to move around and you start to interact with other people. Well, same with solid. Same with the solid phase. All seats are taken, so you don't move that much. As I said, we have water, which is in the liquid phase. This is just the regular water that's in your glass. The molecules move relative to each other and do not have a fixed position. The particles attract each other not as strong as in a solid. So why is this the case? Well, when you have liquid water, it's a little bit more warm, the temperature is higher, so the particles move more. And if they move more, they use up more space, and when they have more space, they're a little bit further apart, don't attract each other as strong, and that results in a not fixed position. And what does that mean? That means that water can flow. So if you have a block of ice, the ice is always the same shape. However, if you have a liquid water, it can flow through out of a glass, it can flow over your table, it can flow over your homework and ruin it all. So there's a lot of difference between the liquid phase and the solid phase. Finally, the gas phase. I see I forgot space there. Simple example, water vapor. When you start to boil water, you can see the water vapor rising up from the water. Well, molecules move wherever they want, with much distance between each other, and they don't attract each other. So, gas phase, same as the air around us. There's a lot of free space between the molecules, so we can move through the air with a lot of ease. However, through the liquid phase, if we move through water, if you walk through water, you notice it's very hard. It's like walking through a busy street. You bump into people, everybody has to move out of the way. Well, gas phase, you walk through an empty street at night. Yeah, so the gas phase, not many particles that are close to each other, more further apart. So how does that look in like a visual aspect? Well, I have the three phases here, and I think you all know instinctively which phase is which. So we have the solid phase, all very tightly together. We have the second phase, that's a liquid one, liquid phase. There's a bit more space in between the particles, so they can move out of the way. And you see the last one, the gas phase, which has a lot of space in between. This is also where the density comes around the corner from paragraph 3.2. Yeah? A very high density, a lot of molecules all in the same area. In the liquid phase, a little bit less density, still high, but not as high as the solid one, because there's a couple of empty spaces, so there's not as many molecules as before. And in the gas phase, of course, a very low density. That's why there's because there's a lot of empty space between the particles, and as we said earlier, between molecules there's nothing, so nothing that has a mass. Well, as I said, the three phases, I put it down there as well. And to give you the example of water, well, we have ice, that's that one. Liquid water looks like that. And finally, the gas phase, water vapor, is what you see up here. Well, those were the three phases, and then, as I said, a very, very small topic of mixtures, and I won't talk that much about it because it's very, very easy, and we already talked a little bit about it in paragraph 1. Well, a mixture contains two or more substances, specifically pure substances, and they're distributed through each other. Well, what does that look like? First, in the first paragraph, I showed you this image. Yeah, we have a pure substance here. Consists of two atoms connected to each other. So these are all blue molecules. And then here we have a combination of red and green atoms connected to each other. Yeah, all different, all the same molecules. But this is a different molecule than the first one. So if you mix them together, you can see there becomes you get a mixture. And in the book, they also showed it with a very nice image. You have water molecules far apart. You have sugar molecules all close together like a sugar cube. You add them together and you can see the water molecules and the sugar molecules all spread through each other. So that's what I also want to see if there's a question that asks, well, explain on like a micro level. A micro level is a very small level, microscopic maybe even. You've used a microscope in biology. Microscopic, a very small level. So at the individual molecules, how what does a mixture look like on a micro level? Well, you can see all the molecules are mixed through each other. Well, if I promise you to show you an image, an example of a different molecule, one with carbon as well, and I'm building it right now. This is the first half of it, and I'm almost done with the second half. There we go. And as we said before, the red balls represent oxygen and the black balls represent carbon. So what do you think this molecule represents? It's a very common molecule. I think we've all heard of it because it's been in the news a lot, especially in the last 10 years roughly. It has something to do with climate change. So think of it, post your answers down in the comments and we'll see if you have it correctly. So that was also the finishing part of this course of 3.3. We talked about molecules and atoms, the molecular model, the three phases of which a substance can be exist, and finally, what do mixtures look like on the molecular level? I hope you have learned something from this video, and I'll see you guys next time.